All right, hello everyone, and thanks for joining our Digital Thread series on leveraging a digital twin for innovation and efficiency. We really appreciate you guys spending time with us today and hope you'll find today's topic to be very informative. I would like to mention that we are recording today's session so we can provide a replay to the folks that were unable to join us on the call today. My name is Randy Spivey, and I will be your host for today's session. So let me begin by introducing two of my esteemed colleagues who will be presenting for you today. First is Dave Introcaso, and Dave supports the implementation of digital manufacturing solutions across multiple industries, including heavy equipment. In a previous role, he served as an on-site consultant at an automotive OEM, where he assisted with the global implementation of digital manufacturing methods and best practices. Prior to joining Siemens, Dave supervised and executed various process planning projects for an automotive Tier 1 supplier. Brad Rosenheimer is a portfolio development executive focused on manufacturing operations management for heavy machinery and automotive customers. Brad has been with Siemens for just over a year and comes to Siemens with over 20 years of manufacturing experience, most while employed by Danfoss, a globally diversified manufacturing company and longtime customer of Siemens. Brad has a long history with Danfoss, starting on the shop floor as a college intern and eventually working up through the organization into senior leadership positions. Brad is a graduate of Iowa State University, where he attained a bachelor's degree in computer engineering and a master's degree in systems engineering. So before I hand it over to Brad and Dave, I'd like to just take a few minutes and recap the series and what we mean by the industry digital thread solutions. So in this series, we're going to take you on a journey to explain the value of the digital twin and the 5 industry-specific digital threads across the entire product development, production, and service life cycles. In session 1, we began by presenting Siemens' digitalization strategy and the value the digital twin and digital threads brings to our customers. We concluded with recommendations for getting started on your digitalization journey and the importance of building a compelling business justification and ways in which Siemens can partner with you to help streamline that process. Session 2 was focused on model-based systems engineering and how to address the growing challenges of product complexity in an age where electrical, electronics, and software systems are a key source of product differentiation. Session 3 addressed the challenges of developing complex electromechanical systems and how to accelerate the product development process by integrating the mechanical, electrical, software, and manufacturing engineering disciplines. We also discussed the importance of integrating your verification and validation processes into the mix and the impact it can have on reducing cycle time and improving overall product quality. Today, in session 4, we'll pick up where we left off and get into a deeper dive discussion on how to leverage and enhance the digital twin by cascading the digital thread further downstream into manufacturing. So also, please be sure to join us for our last remaining session on service lifecycle management that will be held on March 3rd. So lastly, I also want to mention the separate session on the left there on predictive performance engineering. Predictive performance engineering is also one of the industry digital threads, but was covered extensively in a separate mini-series back in October. So that series covered a range of topics focused on solving very complex problems from noise and vibration to thermal analysis to electrification and autonomous vehicles. So if you haven't seen those presentations, we encourage you to do so. I will post a link in the chat window so that you can go find the replays of those, of actually this entire series. So we really hope you take advantage of those sessions so that you can get a much more holistic view of the value of these industry solutions that we're talking about. So in the last session, in session 3, Darren Dietz, one of my colleagues, did a really good job. He did a great job actually in defining what we mean by a digital twin and digital thread. So rather than me repeat what he said, I encourage you to go out and take a look at the accelerated equipment design session. And if you can't attend the entire thing, at least, look at the first 5 or 10 minutes. But in a nutshell, I thought I'd recap a little bit. In a nutshell, Darren mentioned that this concept of a digital twin and digital thread is really nothing new, which, any of us that have been around for enough time realize that. We've had much of the technology we're talking about today for decades. One of the key differences, though, is the level of integration that we'll talk about today and that what we've been talking about throughout this series. So what he described is the ability to model, simulate, test, and verify and validate your products, as well as your manufacturing processes and equipment virtually before committing to costly physical prototypes or committing expensive people and production equipment to prove out your product designs and manufacturing processes. So that's an important concept to wrap your head around. So this on the left, these first two bubbles is what we commonly refer to as the virtual world. So we can leverage that knowledge that we glean from the upfront process in the virtual world to produce and service those products more efficiently, cost effectively, and with a higher degree of confidence that we will achieve our expected outcomes, ideally preventing any surprises during production or worse, after products have been placed into service. So once again, the knowledge that we gain from the performance of the products in the field and production, our production processes, can be used upstream to improve the fidelity of our models, to optimize our designs, and continuously improve the manufacturing process. So if done correctly, the benefits can be transformational, leading to higher quality products, increased revenue, greater profit margins, and most importantly, happy customers. So I just want to pause here for a minute and just acknowledge we realize that this is a bit of an idealized view of the world. And one of the questions we commonly get asked is whether you have to replace your existing systems to realize this digital vision. And in most cases, the answer is emphatically no. You don't have to replace your systems. However, there may be some special circumstances or situations. Maybe you've got some homegrown systems or unsupported legacy applications that would, they might cost more to develop an integration rather than migrate to an off-the-shelf solution. So, but this to me is one of the core strengths of Siemens, and as a former customer myself, it really, emphasizes the open by design strategy that Siemens has. So we can help you develop a plan that protects your existing IT investments while still enabling you to realize this digitalization vision and your digitalization goals. So, just bear that in mind. We're very open and we can integrate with most anything that you've got in your current environment. So next, Darren also talked about the importance of fostering better collaboration among all internal and external constituents in the development process. We see here at the top a small subset of an organization, just a representative example. So one of the many challenges that our customers struggle with is having a very departmental or vertically scoped mindset. This often results in making investments in siloed technology solutions, which result in solving very localized business problems. And I'm not saying this to be critical or judgmental or anything, but despite their best intentions, those types of investments typically don't yield the transformational benefits that most companies are looking for. So by contrast, Siemens' strategy is to enable integration of the people, processes, data, and technology solutions horizontally across the digital enterprise, breaking down the departmental barriers that often negatively impact manufacturing companies, resulting in delays or project overruns, scrap, rework, and, potentially inflated warranty costs. So what we find, and others that I'll cite in a minute, companies that embrace a digitalization strategy and enable a digital thread achieve far greater benefits than companies investing in localized point solutions. So as a case in point, I want to share a fairly recent study done by Tech Clarity back in 2019. And in this study, they surveyed 150 companies to gauge the importance that digitalization has on business strategy and business performance. So on the left, you can see that combined 64% of the respondents believe digitalization is either critical, shown there in red, or important, shown in blue, to achieving their business strategy goals. In addition, the graph on the right, we see that companies successfully adopting a digitalization strategy have realized a 31% improvement in revenue and 25% margin growth over a 2-year period. So I don't know about you, but I really think that those are very impressive numbers. It really shows how important digitalization is to companies these days. Now, in addition to this, I also cited an example of one of Siemens' own experiences with digitalization at one of our divisions in session 2. You may want to check that out. And it was on the model-based systems engineering session. The results that we've seen within our own manufacturing facilities is quite staggering. So hopefully this gave you a little insight into how we define a digital twin and the digital threads. So without further ado, let me turn it over to Brad.
All right, thanks, Randy. So I guess I wanted to cover a little bit of the agenda of what we're going to go over today, and then from there get into our discussion around smart manufacturing. So there'll be a short introduction, and then we'll talk about what manufacturing smart decisions means. So whenever I think of smart manufacturing, I very much think about all of the decisions that need to be made to drive you to your best self. And as we talk through that, you'll see what I mean. We'll go into how manufacturing engineering decisions are driven with the products and services that Siemens has, and then we'll talk about manufacturing operations management decisions. We'll look if there's questions and answers at that point, and then go through a little bit of a summary. I'd like to start out by thanking everyone actually for their efforts in fighting COVID over the last year. So many of us and everyone here have sacrificed and gone to extreme efforts, either direct or indirect, and I want to ensure I convey my gratefulness towards everyone contributing. We've all done things related to how we manage our shifts, where we work from, the different devices that we have to wear, or how often that we take precautions related to hand washing and different things. And every small effort and progress that we make to return ourselves to that normal state where we can again travel and live our lives in a normal way as much as possible is an accomplishment and a welcome change. And I guess I want to express my gratefulness towards everyone in that. And so with that, I think many of you, like myself, were eager for the new year, anticipating a different trajectory for the year with hopefully more positives than negatives, looking forward to doing things that we took for granted in the past. Along with the new year comes the annual tradition of New Year's resolutions. This is often partnered with a message of becoming the best version of yourself. Typical goals are often centered around exercise or health, relationships, or education. Perhaps you plan to run a marathon this year, or maybe you plan to go back to school or take on a really difficult hands-on project. All of this in an effort to become, the best version of yourself. These are not easy decisions to make because you have limited time, limited money to apply to these goals. And if you choose too many, you'll never reach any of them. So what does any of that have to do with smart manufacturing? I think there's a lot of similarities between the theme of becoming the best version of yourself and becoming the best manufacturing version of yourself. So just like you go about choosing what your personal goals are for the year, so too does your manufacturing organization choose its enterprise goals. Just like a goal to improve an aspect of your health so too does your organization attempt to apply continuous improvement to improve the profit margins of their products. Just like the goal to expand your skills, so too does your manufacturing organization attempt to build more variable products to expand their market share or increase their product volume. Just like you have limited resources to apply to your journey of continuous improvement, so too does your manufacturing organization have limited resources. And ultimately, just like the journey to be the best version of yourself is never ending, your manufacturing organization's journey to be the best version of itself is also never ending. I think the analogy extends further still. Many studies have shown when you make these personal goals, a critical step is to break them down into smaller deliverables. If you never break them down and only focus on the end goal, your likelihood of success is extremely low. When you break them down into small pieces and transition them into smaller steps, they become accomplishable. Each one of these deliverables is a point of decision. The same concept is entirely applicable to manufacturing. Each goal is broken down into smaller deliverables and contributes to the overall goal, ultimately delivering a better version of your organization. The responsibility you have to deliver in these situations can be daunting, as your deliverables have such a strong contribution to your future. The decisions that you make to improve the organization ultimately determines your organization's competitiveness in your market. The decisions you make determine your capability to deliver a product that fully satisfies all your customers. The decisions you make determine how well your employees engage. They affect your employee satisfaction and ultimately your company culture. When an individual chooses what goals to take on, envisioning the outcomes is critical to their success. The more detailed these visions are, the more likely you are to realize the goal. Tiger Woods doesn't imagine hitting the green. He imagines hitting the green in an exact location with a particular rate of spin from a particular angle. Do you imagine your manufacturing outcomes the same way? How do you know when the details of your visions is sufficient to deliver to your goals? Modeling these outcomes and bringing transparency to your process is a complex problem to solve to deliver these goals. Can you deliver on these decisions? So let's break down decision-making a little bit more. What decisions are being made? They're supply chain decisions. How do you handle specific supply chain disruptions? Have you ever achieved your optimal, how do you achieve your optimal manufacturing footprint and layout? How do you validate your manufacturing plan? How do you do verification studies? Maybe they're process decisions. How must I break down a process to maintain takt time across a particular product mix? Who is making your decisions? Do you realize who is making your decisions? Are they being made at the shop floor level, at the process engineer level, at the design level, or are the wrong people making the wrong decisions? Who makes tactical decisions? Who makes the strategic decisions? Do you have the right people enabled to make the right decisions? So when a decision needs made on the shop floor on a Saturday night, are they enabled to do so? Has that been modeled in such a way that it's a predictable outcome? How would that impact so is it possible to enable more people to make more decisions sooner? How would that impact your business and your company culture toward ownership? Where are your decisions being made? Are your decisions being made with all the impacted stakeholders? Do you make decisions and then run into problems executing the decisions due to missing stakeholder buy-in? When are your decisions being made? Are you constantly struggling to adapt, or are you primarily making reactive decisions? How are your decisions being made? Are you making your decisions all with your gut? Have you defined a guiding strategy to follow? Have you sufficiently modeled and done what-if planning to predict potential future states, thus enabling faster decision when those modeled situations are a reality? Wikipedia has a long definition of smart manufacturing, and you want to do it all. Everyone wants entirely computer-aided manufacturing and high levels of adaptability. They want to be able to make fast changes based on demand. They want to have an optimized supply chain, leveraging 3PLs. They want efficient production and systems to be interoperable. But taking on everything at once is exhausting and honestly not accomplishable. So you have to strategically decide where the best opportunities exist to invest in your end-to-end life cycle. So this is your starting point, determining your best opportunities. So you engage your lean experts to find opportunities for continuous improvement. Where's the waste? Where's the potential for value? Perhaps you employ lean tools to build a value stream map to identify opportunities. Perhaps you look at your in-process inventories and are focused on improving your inventory turns per year, reducing your overhead. Regardless, you find your starting point. So from here, you have to do some analysis to determine the right next steps. This can be time-consuming and exhaustive. How can you be confident the improvements being proposed are sufficient to deliver to your end goals? When do you achieve your due diligence? This is where Siemens manufacturing engineering products and manufacturing operations management products deliver great value, answering the hardest questions, leading to the best decisions. At this point, I'm going to hand it over to Dave to further elaborate on the decisions within the manufacturing area that really can drive you to your most competitive position.
Okay, thanks, Brad. So when we get into this area of smart manufacturing, the whole idea here to be able to make these smart decisions, to be able to accomplish this ideal of smart manufacturing is to be able to, enable effective collaboration throughout the life cycle. And, we feel that there are some key enablers to being able to do this. One is the digital thread that Randy spoke on at the beginning of this session, right? This idea of being able to leverage the same information across the entire life cycle from design to execution and beyond, even into, service areas. The second is being able to have best practices for complexity management. And this is especially critical in an industry such as this, like a heavy equipment area where we're dealing with a lot of configure to order type scenarios. And then the third idea is to have closed loop manufacturing. And what we mean by that is, it's one thing to have the digital twin to be able to cascade common information across the life cycle. But then can we even take it one step further from that and enable, feedback loops at each step, right? So not just one-way sharing of information, but a closed loop back to be able to, gain some insights, from what's happened, being able to give that feedback, back downstream to be able to, enable, again, smart decisions. So, this here is kind of an alternate view of, again, what Randy spoke about in the beginning, right? A similar view with having, in this case, showing walls up between these different disciplines and these different areas of the product life cycle. And, as Randy mentioned, right, you might have different systems. And the idea is, of course, these systems would be in reality today, in a lot of cases, disconnected from each other. So you get this, throwing over the wall idea of things. And again, no visibility into what the other group is doing, things being done, only vertically integrated, not horizontally integrated. What we're going to hopefully show you here today is some ways in which we can actually start to remove these walls and enable this idea of collaboration and smart manufacturing. When we talk about the product life cycle and we go starting at product development into manufacturing and then into, utilization and performance, the manufacturing area in the middle, digital manufacturing, is really, can be split up into two areas. Okay, so we have manufacturing engineering, which a lot of people would refer to as manufacturing planning. And then you have the manufacturing operations, which is the execution side of it. So from my side here, I'm going to show you some examples on the manufacturing engineering side of things. And then from there, Brad is going to go a little bit more into the manufacturing operations piece. And now for the manufacturing engineering area, as I said, this manufacturing engineering or manufacturing planning kind of sits in between, product design and manufacturing execution. And what it really does is it bridges the gap between the two of those aspects, those areas of the life cycle. So the typical things we're talking about in this domain are things like developing a manufacturing bill of materials, developing a manufacturing bill of process, which is the process planning aspect, And then, of course, after we develop a plan, we want to validate it. So being able to do some validation to that process, being able to optimize our line design, and then some additional, simulation and commissioning aspects are also available beyond just the normal simulation, right? Virtual commissioning, for example, controls logic as well in a virtual environment. Being able to debug all of our controls logic, up front in the virtual world before a ramp up on the production floor. And then, of course, flowing throughout these, we had the ideas of model-based quality and manufacturing data and change management, which are critical, to be managed throughout the whole entire life cycle. And again, what we're going to show when we go through some of these examples is this idea of the digital twin. And when we show the examples, what we're going to show is, we refer to it as a holistic digital twin, because a lot of times when the term digital twin is used, people are thinking only of a product-based digital twin, right? A twin, of your product in the CAD data. What we're also going to show you examples of are productions of a digital twin of the process and a digital twin of your production environment itself. Okay, because this is what really compromises a holistic digital twin. So, getting into this idea of making smart decisions. What again I'm going to do is take you through some examples of typical decisions that you might have to make, throughout the course of a day, on the manufacturing side of things. So the first example we're looking at is, on the manufacturing side of things, can this design that I'm getting from product design actually be manufactured in a repeatable manner and in a robust manner on the shop floor? What you're looking at here is, first of all, somebody on the product design side, and they've designed, in this case, it's a new axle for a new tractor. I don't know, somebody might want to go on mute. I'm hearing some background noise. In this case, the product design person here has designed a new axle for this tractor, some new brakes, and what they want to do is kick off a design for manufacturing study to the manufacturing side of the house and say, hey, can you have a look at this? We've designed some new parts here, again, the brakes in this case, and we want to see, we want to get, again, some early input from manufacturing as to, whether this can be done and produced, manufactured efficiently. So what the person on the product design side has done in this case is kick off something called a workflow. And when they kick off this workflow, now what you're seeing is somebody on the manufacturing side of things. So this is a manufacturing engineering role, and you're seeing what they would see as they start their day here. So they kind of log in and see, okay, I see this workflow. All the steps in green have been performed. Now it's to the box in yellow, which is saying a manufacturability analysis has to be performed here. So that's the task of this manufacturing engineer. You can see also what they have the ability to do is look at the parts that were attached to that workflow, to this request that they're getting. So they can see they're being asked to look at some design for manufacturing for these new brakes that were designed for this tractor. And now what the person on the manufacturing side can do is actually go in and perform their analysis and, make that determination as to how they feel about the design. You saw there, we turned on some of the PMI, and that's one of the things that's, kind of one of the first examples of leveraging some of this information downstream. So that was PMI information that was, created by product design, visible by manufacturing here. And in this case, what we're doing is the manufacturing person responsible for doing this DFM study is going to perform a tolerance stack-up analysis of this brake build operation. So they're going through and performing a simulation of basically 1,000 different builds of these brakes. Again, leveraging not only the digital twin of the product, but also the PMI information that was created up front. And they're going to basically run through this analysis to determine, come to that decision that they have to make of, yes, we do give the buy-in from this on the manufacturing side, or, we see maybe a potential issue here. Can you go back and have another look at it? So we're finishing up the analysis on the study. So again, this was a kind of what we call a variation analysis study. It's a tolerance stack-up analysis study. You can see as we look at some of the results here that we are at a spec in one particular area here. So when it comes now back to this workflow, what the person on the manufacturing side can do is attach a report of their study to the workflow. And then they come to this kind of decision box, right? This is all about manufacturing decisions. Do I give approval or not? In this case, they want to go in and say, hey, we saw something out of spec here. Can you please go back and take another crack at this on the design side, before we go ahead and try and actually start to build this thing. So again, an example of a smart manufacturing decision being made here upfront in the virtual process, while manufacturing still has the ability to influence the product design. That's one of the key aspects of this here is manufacturing getting involved early in the process before the design is finalized. Okay. Now, the next piece we want to look at is when at the point that we do have a finalized design, now in the manufacturing planning side of things again, how do we make sure that we're accounting for this in our bill of process, in our production plan, in our routings? So what you're seeing here is at the top of the screen, a manufacturing bill of materials for this axle. And what you're seeing at the bottom of the screen is a bill of process for the axle, all of the operations that would be necessary to actually, build up these brakes on this axle on the shop floor. And of course, on the right-hand side of the screen, again, you're seeing another example of a digital twin. In this case, a digital twin of the product itself, this front axle. So what the person on the manufacturing planning side here is doing is creating some new operations for this brake build. In this case, we're creating some brand new operations because it happens to be some new brakes that were designed. One of the key things to remember here, though, is that we can also have libraries of standard operations that we can leverage and basically reuse over and over, especially coming in handy if we're building the same product in multiple plants. Okay, so what we've done here is we've created operations. You can see we've got one operation to obtain the calipers and mount them, and then another one to secure them with the power tool. We've got 2 operations on the left side and 2 on the right. And what you're seeing now is this mapping that's been created between the bill of materials and the bill of process. You see by these numbers in this position designator column, that's indicating, where these parts should go in the bill of process. So when we run this command here called resolve logical part assignments, you see what's been done is it's assigned these parts to that operation. Again, it's a kind of a smart feature here. It knows by this mapping that was created, basically, where these parts should go in the routing. Okay, so we ran it for the brakes. You see the brakes show up there on the bottom right, and then we can, similarly run that same command for the entire axle, because again, the idea here is let's make sure we account for every part in our production plan, so we can do that and ensure that basically all of our parts have been assigned somewhere in the bill of process. There's a routing for everything. Last thing we're looking at here is an example of another kind of smart piece of functionality here that we have called a tool requirement. So when we click on this bolt that needs to be secured when we're installing these calipers, there is a requirement on the manufacturing side for a tool. And in this case, we need, as you're seeing here, a power tool. So we can go in and through this classification structure, specify that anywhere we have this operation, we need a power tool with a maximum torque greater than or equal to a specific value, whatever the value is for that operation. And once we do that and define it here, you'll see that in this assignments area in the middle here, this tool requirement has now been assigned to that process. And what that means is basically anywhere we move that process in the manufacturing facility, the requirement for that tool is going to go along with it for the ride. So we never lose track of what tools we need to perform that operation, no matter where it's done on the line and no matter what assembly plant we're carrying it out in. So third example we want to look at is, now we've kind of planned, the process. What we want to do now is validate it. So now here's where a digital twin of the process itself comes into play. So in this case, what we're doing is performing a simulation, an ergonomic simulation of this brake build of, again, securing these calipers here to this front axle. This is our simulation environment, but the nice thing to remember here is, again, this whole aspect of, being horizontally integrated. The bill of process that you see on the left there has been, carried over from our planning tool. Okay, so when it comes time to do the simulation, we don't have to, recreate the bill of process. We're basically leveraging the bill of process information into the simulation environment. And likewise with the 3D data that we're seeing here, the CAD data, the digital twin of the product itself, being leveraged from the planning aspects we did earlier, right? So from that, we've created a digital twin of the process. We're simulating here the operation from an ergonomic standpoint. We're looking at some of the analysis tools here, so you can see, in this case, some of the strain on the operator, on the different joints. So you can see that when the operator is performing the secure with the power tool, there's a strain on the wrist. Now we're looking at something called the force solver, which will give us an indication of basically how much force does this operator have to apply when they're holding that caliper in place for the loose install operation. And again, is it within ergonomically acceptable limits? And of course, anytime we do a human study like this, an ergonomic study, one of the things we want to look at is the reach range. So we have the ability to turn on this reach envelope for the operator and make sure that they can reach everywhere they have to for the operation. And then similarly to the reach, we want to look at, of course, the vision. So we can turn on something here called a vision window and basically see the operation through the eyes of the operator, again, ensuring it's not a blind operation. What you're seeing here is a 5th percentile female model. Now we've just swapped it out here with a 95th percentile male model. So we can run the simulation for the entire range of operators that we might have and ensure that it's ergonomically acceptable for everyone, okay? So again, a very key decision to make there, right? Again, this is gonna validate, can we do it, but also, is it ergonomically acceptable, for an operator? Next example I wanna look at is, so we've kind of created a plan, we've validated a plan, we've created this process data. Now what we wanna do is, decide, can an operator on the shop floor assemble this? How are they gonna know what to do? And, is it going to be clear to them what they have to do to actually carry out the steps of assembling this brake build on the floor here? So what you're seeing here is basically authoring of electronic work instructions. So again, leveraging that same bill of process, leveraging that same digital twin of the product, and you can see all of the different information that we have here available to present to an operator on the floor. You're seeing the list of steps there. You're seeing the list of parts that are required, the resources, which would be the tools. And of course, what we're doing now is showing some markups and some attachments that we can create. You see, again, some nice smart functionality when we type these brackets, these 2 square brackets, and a list of the parts pops up there on the screen. And so the nice thing about this is, it eliminates, data entry errors. You don't have to worry about typing the name of a part, these complex names. Basically, you can type these 2 brackets. It'll pop up for you the parts list automatically, and then you can just select the applicable one and populate it. So that's kind of building out the steps that the operator would have to perform. And then, so we've saved that. And then, again, we're going to include some more visuals here, right? So we can attach some JPEGs like you saw. We can also attach some movies. And in this case, what we're doing is attaching a video of that simulation we just did. Okay, so another example of leveraging information downstream, leveraging the validation work that we did now into the work instruction, right? So we've attached the video, we've attached a couple more JPEGs. Now, if we go and actually refresh this, right? So this is kind of what it looked at before. Now we're going to reload the page and see basically what it will look like for now an operator on the shop floor, right? So an operator logging in, looking at the work instruction, this is what they would see. Again, the steps, the parts, the tools, and also the visuals, right? So again, playing that movie that we just made, leveraging that same simulation. So an operator can, reference the written steps. They can reference some of the other visuals. They can reference the required parts and tools. And they can also watch this video and say, okay, this is exactly how I should be carrying out this operation here when I'm doing it on the shop floor. Okay. Now, one final example to look at. So we've looked at examples of, digital twin of the product so far. We just looked at a digital twin of the process with the ergonomic simulation. Now we want to look at a digital twin of our production environment. Okay, so starting here with this sub-assembly line that's manufacturing these axles on the floor here. We've got a model of our production, and you can see we're going to run a simulation here building a certain model mix of 3 different variants of the axle, A, B, and C. So we put the model mix in there, the percentage of each, and we can run a simulation here and see basically, what our throughput is going to be, basically how many axles can we build per day based on that model mix that we just defined and based on our bill of process. Now, what you can see is we're going in and changing these numbers. So now instead if we build 10% A, 20% B, and 70% C, we're changing the model mix. What is this going to do now to our production throughput? So again, enabling us to make a key decision here, right? Can we meet the throughput if we rebalance the model mix? So this is a great example of the what if type of analysis and what if studies that were referenced earlier, okay? This is a discrete event simulation tool, and this type of what if analysis is exactly what it's great for, is being able to put in these kind of hypothetical parameters and see how our real system would respond to those parameters without having to shut down the real system and actually execute it on the shop floor to see what the results would be. Okay, again, being able to do everything up front and being able to do it in parallel to the actual production, because again, we're leveraging a digital twin of the production here, not the production itself. The last thing you're seeing here is we have the ability to do this in 2D as well. So we didn't want to kind of overwhelm everyone and make you think that you have to have this detailed 3D model of your facility. It has gotten a little easier to do that with scanning technologies here in recent times. But if you don't have all the 3D data for your facility, you can just as easily build a 2D model, a 2D representation of your production with the same parameters, and execute a very similar discrete event simulation study with the 2D model like you're seeing here, and run the same type of study. Change your throughput. You can look at changing cycle times. You can look at adding or removing stations, adding or removing workers, all kinds of different what if studies that we can do by changing parameters. And then lastly, of course, we've been focusing on this area of the tractor around just the axle. Of course, we can extend that now back to the entire tractor itself, right? So how many tractors can we build a day, in our facility? Again, based on the parameters of our model and our production digital twin. And again, there's a lot of different things we can look at here. So in this particular example, we're looking at worker utilization, right? So we can see how many workers are, fully utilized here, how much time they spend, doing each of these tasks, right? Setting up, preparing, walking to job, waiting, all of these different things. So, that's really another example of what we can do with this type of discrete event simulation. Okay, so again, that was kind of the manufacturing planning side of things. What I'm going to do now is turn it back over to Brad. And Brad is going to continue on with the MOM side of things, the more manufacturing execution piece of things.
Thanks, Dave. So as we think about manufacturing operations management, we're going to switch now from the virtual space to the real production area. So MOM becomes our focus in the digital enterprise. So from here on through execution, MOM becomes the centerpiece of the environment. People, processes, and tools are combined to either push or pull production through the environment with a focus on efficiency and quality. Tracking of your execution gives you the data and feedback loops that are necessary to drive continuous improvement activities in your production areas. So as we consider the component of the MOM platform, it provides a set of lifecycle and manufacturing services that transform your current operations into a digital version of the smart manufacturing. Your smart shop floor will be connected with real-time collaboration by continuously pulling traditional data sets along with new sensor and location-based data sets. You'll have real-time data enabling collaboration with suppliers and customers to enable third-party logistics or a Kanban-based delivery methodology if you so choose. Your smart shop floor will be optimized with automated and reliable operations. You'll have reliable, predictable production capacity. You'll have increased asset uptime and production efficiency. You'll drive highly automated production and material handling with minimum human intervention, only as necessary per your requirements. And then minimize cost of quality and production. So being able to deliver your products with the highest quality product with the least investment to accomplish it. You'll bring transparency to your shop floor through real-time data intelligence. You'll have live metrics and tools to support quick decisions. You'll have real-time linkage to customer demand forecasts, and you'll drive transparent customer order tracking. Your smart shop floor will be proactive. You'll be able to anticipate and act before issues or challenges occur. You'll have predictive anomaly identification and resolution. So you'll be able to determine when those things are occurring or will occur before they've occurred. You'll also have automated restocking and replenishment. Your smart shop floor will be agile by having smart and flexible workplaces to quickly deploy process changes. You'll have flexible and adaptable scheduling and changeovers. You'll have implementation of product changes to see impact in real time and have configurable factory layouts and equipment that give you the flexibility to maximize your density on your shop floor. So the MOM portfolio today is developed to provide quality tracking during manufacturing operations management execution. It's developed to provide advanced planning and scheduling to drive optimized customer deliverables. It's developed to provide manufacturing execution systems to deliver execution consistency. From that consistency is what delivers your best customer outcomes to drive trust. The MOM portfolio is developed to provide RD&L to manage lab environments for prototype management, for performance testing or endurance testing. And the MOM portfolio is also developed to provide enterprise manufacturing intelligence, really bringing actionable content to at the right time to the right people. These functionalities can either be in the cloud or on-premise, depending on the needs and strategy of your organization. So let's take an in-depth look at the role of MOM. So how do I transform virtual production into efficiently orchestrated operations? Thanks to Siemens MOM and integration with PLM and ERP systems, we're able to transform virtual production and production orders into real production execution. MOM collects the bill of material and the bill of process from PLM and the production orders from ERP. MOM's advanced planning and scheduling compares all of this information from PLM and ERP with real-time information from the shop floor, such as machine availability or maintenance status, etc., and generates an optimized production schedule. Then MOM orchestrates all manufacturing and quality operations according to the production plan. This activates the right machine with the right operator at the right time for the right activity. With the same logic, MOM is capable of synchronizing all manufacturing operations with automated and flexible logistics. Logistics such as inventory kitting operations or material handling can be driven at the shop floor through just-in-sequence or Kanban-based methodologies. Automation can be integrated to deliver the right product at the right time through AGV technologies or other cart systems. Matrix-based assembly processes can be managed in a pull-type scenario to drive customer orders when that type of setup is also necessary to best manage the efficiency and uptime of your operations? How do I ensure my build is going according to plan? While orchestrating all manufacturing and quality operations, the Siemens Manufacturing Operations Management Solutions collect data from the shop floor and contextualizes it by adding detailed manufacturing and quality information. Smart data contextualization is about enriching data with context coming from the MOM system or any other manufacturing intelligence data source. That data source could be an application you've developed in-house. It could be multiple ERP systems that you've got in use. It could be a SCADA system on the shop floor. Regardless, we have the capability to bring all of that data together to make great decisions. How do I ensure current product quality and leverage that knowledge to improve future versions? Thanks to the digital thread between MOM and PLM, or even through cloud technologies, we're able to distribute the actionable information at the right time to the right department. In this way, we enable closed-loop manufacturing and closed-loop quality. Closed-loop manufacturing enables firms to synchronize and optimize production across product design, production planning, manufacturing execution, and intelligence from consumer use in the field. Creating a collaborative, connected information loop, CLM continuously improves the cost, time, and quality of the manufacturing process to accelerate the delivery of products at the optimal level of quality and cost. Using CLM tightens the alignment of the as-planned product with the as-built and as-used product in a continuous and iterative process. Closely coupled with CLM is closed-loop quality. While the focus of closed-loop manufacturing is on synchronizing highly efficient production of the current product, the focus of closed-loop quality is on improving the quality of the product across the entire product lifecycle. Closed-loop quality is a continuous process of plan, do, check, act, evaluating the quality of the product at each stage of the product's ideation, realization, and utilization, and feeding quality information back into the production and design processes. Its purpose is to ensure the quality of the current product and feed intelligence back into design to improve the quality of the next generation product. Closed-loop manufacturing is essential for a manufacturing enterprise to thrive in this new area of smart manufacturing, and it is a cornerstone of the digitalization journey. CLM supports closed-loop quality. The two cannot exist in isolation. How do I manage my operations from anywhere? Siemens MOM solutions are smart device ready. Siemens MOM software has a responsive and adaptive user interface enabled for multiple devices, tablets or smartphones, that provides access to manufacturing data for real-time on-premise visibility or off-site visibility with performance indicators and high-level production KPIs. How do I ensure I have fully leveraged my organization's capability and capacity? Siemens also has unique cloud-based capabilities with MindSphere, with the first aim to share production data through cloud. Plant data is collected from different systems, whether that's tag-based, relational databases, enterprise applications, etc., and consolidated into a unified data structure where it can be referenced to drive KPIs at any level. They can be at the device or asset level for OEE type reporting. It can be at the assembly line or supply chain level to provide a plant-centric viewpoint, or it can be at the enterprise level to validate production capacity across multiple plants. This provides a framework for operational, tactical, and strategic decisions at every company level. So as we think about smart manufacturing and the complex set of decisions that need made, we need to consider the whole system to properly optimize the output. This requires close collaboration between organizational departments that can't be accomplished when working separately. So as we bring logic to how we work together, this leads to the creation of a shared set of tangible content that, when tied together, drives significantly improved outcomes. This is what we call a connected digital thread for the entire life cycle. At some point, we all realize that becoming the best version of ourselves is really about embracing the journey of being the best version of yourself. So too must we embrace the concept for smart manufacturing. This journey never ends. For the journey, Siemens is your partner of choice with the largest portfolio of functionality to optimize every aspect of your operation.
Hey, Brad, thanks to you and Dave both for sharing those presentations. A lot of great information there. So I guess I'll just quickly recap the series or display the series here. I do want to remind everybody, we do have our next session on service lifecycle management. We've got a special guest speaker from one of our customers. We encourage you to take advantage of that session if you're available. And I did post the link in the chat window to this series. There's a landing page out there where you can go sign up and replay any of these on-demand sessions. So again, we hope you take advantage of all the wisdom that's been imparted throughout this series. So I guess with that, let's conclude today's session, and we really appreciate you taking time and hope that you found this to be helpful. Thanks, everybody.